Hi, and welcome to our Introduction to Machine Learning lecture. My name is Ben Bischel, and today we'll talk about what supervised regression is and, talk about linear models with L2 loss as kind of a first machine learning model for the task of supervised regression. So we'll introduce the overall concept of linear models and linear regression and expand them further here in this chapter. You'll also understand how these linear regression models are usually minimized, and usually you will use something like the L2 loss. And we can also call this the sum of squares error or the mean squared error or something like this. And we'll understand how the optimization of the L2 loss together with the linear model results in an SSE minimal model. And in general, we also want to do this. I guess many of you might have seen linear models already from a statistical perspective. You're introducing them more from an ML perspective. And on top of introducing very briefly the linear model itself as a model class and how it works, how it behaves like, we want to use this as a template to understand the principle of empirical risk minimization on a simple example, on a simple model class, so we can later on deepen our knowledge regarding empirical risk minimization for more complicated model classes in machine learning. So let's start. What is supervised regression again? So we have a data matrix X, okay? And this data matrix X usually looks like that. And we have N observations and we have P features, right? And then we have here in each row, we have an observation, maybe x1, and here in each column we have a feature vector. Maybe that's the vector of the first feature. Now, in order for us to fix our definition of empirical risk minimization, to kind of make it concrete, we need to define what we mean with the hypothesis space of linear regression. So that's just as we've taught you before, this is nothing more than kind of picking a certain class of parameterized functions and then using them and then later on optimizing them under a certain loss function. So here our hypothesis space is basically as simple as we can imagine it. It's a simple linear combination of features. So we are saying that in order to compute our output, and as we are in supervised regression here, our output will simply be a further numerical column y that we now want to predict given our feature given our feature vectors, right? And the linear regression model does that by adding in a constant offset, which we also call the intercept, and then we simply do something like a scalar coefficient times the feature value plus a scalar coefficient times the feature value plus a scalar coefficient times the feature value. And if we want to, we can also write this in very compact notation. So we use the bold theta here as our parameter vector, and we use the bold x as our collected feature vector. So both would be p or p plus one dimensional, and we use the scalar product of these together to compute our predicted outcome y hat in compact notation in one go, so to speak. And if you're wondering, hey, what has happened with the intercept and why are we just silently dropping this here, I'll discuss this a bit on one of the next slides, okay? And the idea now is to take this model class, take this hypothesis space here, I've just kind of copied it down and set capital H, which is just my formal notation for this collection of all of these parameterized curves. We take this now, and we define a loss function on top of this, and now find the loss optimal parameters to describe the relationship. To find the loss optimal parameters, and if we then plug in these loss optimal parameters into our model, that these hopefully describe kind of an ideal relationship given x and then predicting from x, y, okay? On this prescribed class of potential linear functions, okay? And if you want to kind of get a better visual feeling for how these functions look like, I guess you already know that, but let's just make sure. So in 1D, it would be a straight line, right? Because if we write down the formula in 1D, how would that look like? We have our offset here, or our theta 0, and then we do plus theta 1 times x1, and that's y or y hat, right? I guess maybe let's call it y hat. And all of you guys will have seen this from school. I guess I'm now also drawing the formula behind my head. So maybe let's do it again here. So we have a theta 0 plus theta 1 times x1, and that would be y hat, okay? And this guy here, yeah, this is the intercept. Yeah? So this is this shift here on the vertical axis. And this guy here, this is our slope, right? So for this curve here, this would probably approximately something like 1, I think a little bit less, yeah, something maybe like 0.7, right? And we can also do this in 2D, yeah, and then the model would look like, I guess I'm not going to write this down again, you know, right? This would be theta 0 plus a slope for x1 times x1 plus a slope theta 2 for x2, right? And then we get something like a hyperplane here in terms of our prediction surface. Now, a few words about notation and about the intercept. So I'm basically just spending one complete slide on this topic here, so we can use this as a general trick later on. So as I've told you before, we have this kind of, I don't know, annoying, yeah, I don't know. We have the intercept, and the intercept we have to kind of deal with, in an extra fashion, right? So I probably should have written, even for the compact vector notation, I should have written something like theta transpose times x plus theta 0, and that can become a little bit annoying in derivations later on when formulas become pretty lengthy. And there's kind of a motivation to be able to drop this guy here and silently forget about this. And this is actually possible because there's a neat trick that we can just kind of mentally perform, and this is that we can pad our features with a constant column of ones. So imagine you have your data matrix here, X, yeah, and that would have n rows and p columns, as we are used to it. So n observations and p features. We now just extend it to a p plus 1 dimensional matrix by adding in a constant 1 vector here. And if we now multiply this with theta as a p-dimensional vector, which basically looks like our normal theta, our normal feature vector theta here, and then added in theta 0, so this guy kind of now becomes the intercept is now basically the coefficient, so to speak, for this constant 1 vector here, right? And this this allows us to use the more compact notation like this, right? So whenever I do that, I've kind of used implicitly this padding trick, right? And if you want to, you can also now write down your linear model in complete matrix vector notation. So you can say, let's multiply our design matrix capital X, which looks like this, right? So each row is one feature vector for one observation, and we index the observations here with the superscript. So here we have the first observation, here we have the second observation. You can see the added in ones. Okay, I did this on the left-hand slide, apparently. And we multiply it with this vector. And if we do that, we have neatly in matrix vector notation computed all of our predictions for the complete training set and collected these predictions here in this vector bold Y. And this trick, I will allow myself to use it later again for many other models and not mention this fact a lot more, right? So whenever I'm dropping the intercept, I'm doing this because of this, or maybe also a little bit because of laziness. Okay, so let's look into more interesting stuff regarding the linear model. So maybe a few comments on why the linear model is so popular in applications where we care a lot about interpretability. So the feature effects of the linear model are immediately interpretable, right? Because of its linear structure. So if we increase x1 by 1 unit, the coefficient so if we increase, let's say, feature xj by 1 unit, right? So if we do something like this here, we have our feature x1 or xj or whatever, and we go one step to the right-hand side. So we increase maybe, for example, our age by 1 unit, if age is an input, then the coefficient theta j tells us how this effect of 1 unit translates to the change in the predicted outcome, right? So this would mean that if the coefficient here, for example, I guess, no, maybe let's take exactly the coefficient that we have here in this picture. So this might be something like 0.5, right? So if we here increase x1 by 1 unit, then the outcome would change by 0.5 units. And there's this underlying, what we call in Latin, the ceteris paribus assumption. So this basically means we increase x1 by 1 unit by keeping everything else fixed. And that actually makes sense and is kind of a valid assumption, is a direct, implication and function of the linear structure of our linear model, right? And if you would fit such a model, for example, in R, with the LM function, you can now directly read off the estimates here for your intercepts and for your x1. And looks like I was at least approximately correct with the 0.5 by reading it off from the graph. And you can now directly start interpreting that. Of course, you can do a lot more. You can look at the p-values and so on and start discussing whether features are significant, whether they are, you can compute confidence intervals, discuss the relevancy of these features for your current prediction task. I don't want to do this here because this is not a not a deep dive lecture on the statistical usage of the linear model, but we more want to talk about its I don't know, machine learning properties, or we will just want to kind of handle it from a machine learning perspective, and that means empirical risk minimization. This is what I want to explain to you here now, which is what we will do exactly here on the next upcoming slides. So how do we now determine the optimal set of parameters for our linear model? So as I've told you before, the first thing we need to do is we need to define how we measure our errors, okay? We need to define a little function L, our so-called loss function, which simply measures the discrepancy between our predictions, which would be this guy here, so f of x, and our true labels y, right? And one thing we could do is we can just compute the difference. I guess that makes intuitive sense. See how far we are off, and that difference would be signed, right? It can be positive and it can be negative. And now we want to get rid of that sign, right? Usually, if we don't have any extra information, I guess we want to either over or under predictions, or we want to kind of handle them symmetrically, right? We don't care whether we overpredict or we underpredict. Both are errors, and the strength of these errors or the penalization that results from these errors should be as high as the difference is, I guess, to our prediction. And you can already see I'm basically now starting to explain that we could measure the difference like that, right? So compute the difference and then just get rid of the sign. And that would give rise to this absolute value loss function here. And this is something that we call the L1 loss. I'm not going to do this here. We'll do this in an upcoming session. Here I will use the more traditional L2 loss, which is squaring that thing, okay? So I guess maybe let's do this below. So we'll use that function, and that we'll call the least squares loss, or the L2 loss. If you know about norms from maths, that's the underlying reasons why we call it like that, right? So there's the L1 norm, the L2 norm, and so on. And this is basically the L1 norm and the L2 norm on scalars. So why do we penalize residuals quadratically? I guess if you see something like this for the first time, computing the absolute value might make a bit more natural sense. The reason will become a little bit clearer later. So I guess listen now to this here until the end. Take a look at the L1 session where we talk about L1 linear regression, And then hopefully this is becomes a bit clearer. I want to foreshadow this a bit already here. So what we will see is that, first of all, using the L2 loss will result in an optimization problem in our empirical risk minimization, which is much easier to handle. So first of all, it will be a smooth differentiable error surface that we are going to optimize, and we'll even figure out the resulting cost function as a quadratic form, so we can even solve that analytically and don't have to use numerical procedures. If we use L1, this is way more complicated and harder to handle. It's not impossible, but it's more it's computationally more intensive, a bit more difficult, and there are also different theoretical reasons why the L2 loss might be interesting. Not saying that it always should be preferable, but we can also theoretically connect the L2 loss to the assumption of a Gaussian distribution on our errors, right? So at the end, it's a choice you have to make. You have to choose your loss function as you have to choose your model structure, your hypothesis space, and these choices will have different results and implications for your models. And one can usually not say that one of the two is better. I'm using L2 loss here because that's what we traditionally have been using when these models came about, and because, it's also, I guess, it's a bit harder to motivate, but then it's a lot easier to handle in the upcoming months. So, the next thing I want to show is that we can also visualize these loss functions, and also doing that here kind of as a template, because we'll do this again and again later on for regression, but also for classification. So one way to visualize the loss function is to kind of just plot a one-dimensional input space model here. We know that this is a straight line. Then we can take a look at some data point, maybe this guy here, right? And we can actually, no. Actually, we are looking at our data point here, at this guy. And now we are taking a look at our prediction, which won't be here. And then we have a look at the difference, which is the residual, right? And the residual is usually this signed difference between our true label y minus the prediction f, okay? And we now have to somehow convert this residual into our loss. And for L2 loss, we simply now square this, right? And this is also visualized here on the left-hand side. So we can do this for this guy, or we can do this for another observation where our prediction is a bit far off. And then you can see how the area of that square grows. Yeah, and obviously it grows quadratically now in the residual, which means larger errors are penalized much more heavily. And maybe a bit more informative way to visually describe these loss functions is with these loss plots, where we put our residual here on the x1 axis and the L value, the loss value, on the x2 axis, right? Because on the left-hand side, we can only do this for one-dimensional feature spaces, and we are kind of disentangling this from the dimensionality of the input space. So this is drawn, so the loss function here is simply drawn, it's not rocket science, simply drawn as a function of the residual, right? And here you can now also nicely see how we penalize larger residuals much more strongly because of this quadratic shape of our loss curve, okay? You can also see it's symmetric, and the better you become in machine learning, the more properties you can actually grasp simply by looking at these visualizations of these loss plots, okay? So if I see a visualization like that for a certain loss function, I very often have can immediately see what properties the underlying optimization problem might have, or certain problems that might occur. You can usually get a good idea of how outliers are handled, or how this is potentially connected to certain assumptions or error distributions. And we'll not be able to do this immediately now, but hopefully you can do this at the end of this lecture, or the end of the later, more theoretical parts of our lecture here. Now, can we now write down the complete optimization problem? Yes, we can. So we can now write down our empirical risk. We call this R or Remp, and we usually write this down in terms of our parameter vector theta. And we know that this is a sum across all of our data sets. Yeah, so we go from I equals 1 to n. Yeah, so sum up all of the losses over our complete data sets. And what we do is we now simply, for each data point, we compute the prediction, we compare it with the true label, compute the difference, so the signed residual, and at the end we compute our loss, which is here simply squaring our residuals. And as we could also write it down like that, I guess, so we can write from I to n, maybe something like this, yeah. So we square our residuals. Some people also like to call this the sum of squared errors. Yeah? Some people like to put a 1 divided by n in front of this and then call this the MSE, so the mean squared error. So there are many different terms for this. I usually in this lecture here, I work very often with the non-average version. So I usually use this guy. And for average stuff, I call this R bar. Yeah? But because we now want to mainly optimize for the optimal vector of parameters, we don't really care about these constants here in terms of optimization, right? Good. So how can we now envision what happens when we begin to optimize that? So maybe you guys have not had any formal introduction to numerical optimization. So let me maybe give you some lightweight intro here, how we could envision how this empirical risk minimization now works. So how about we simply try out different models, so different parameterizations of our theta, and then compute their SSE. So we've done this for one vector. I guess maybe we can even try to maybe on the slides we haven't written down how the exact theta values look like. I think they are on an upcoming slide, but we can read them off here from the visualization, right? So for this guy, it would probably be something like theta 0 equals, I don't know, let's say 1.8 maybe. Yeah, that's our intercept here. And we have a slope of what? I don't know, let's say something like, I don't know, 0.5. I'm too lazy to check the exact numbers now. So we maybe try I don't know, arbitrarily we try out that model. It gives rise to such a prediction surface here. And now over our complete training data set, we can compute the SSE. We can do this for a second guy, and this gives rise to a different SSE. And we can already see, well, this guy looks better, right? And now we do this for a third model, and now we say, we might like this even further, right? Because this has an SSE of 10. That's the best we have seen until here. Now, we can start tabulating this, right? And apparently I wasn't completely wrong, at least with the intercept for the first model. So that's 0.8. And with the slope, I was a little bit off, right? That's was a little bit lower than 0.5. It was 0.3. We can start tabulating that. I guess we can now start trying to, I don't know, visualize this a little bit better. So how about we now try to visualize the resulting error surface, right? So what do I mean with error surface? I mean simply the mapping from the theta vector to our SSE value. Well, what's our SSE value? This is just our risk. So, sorry, I'm just visualizing here R of theta, right? And because here I have only two parameters, I can still do that nicely, right? So here I have my intercept. So here I have my theta 0, here for my theta 1, and here I have my risk, right? And now, how will this look like, right? I mean, if you already know a little bit, if you have already thought a little bit about the structure of this thing here, you might have already recognized that this is a quadratic function, right? It's a quadratic function in theta, and this is why we get this bowl-shaped here. So we get this visualization of this quadratic form. And what we can now do is we can now use, we can also visualize our 3 points. So these 3 guys here are these 3 points, and you can nicely now visually see where they are located on this error surface. But instead of now arbitrarily trying out many more points somehow randomly, we of course now use optimization, right? We start at some point, we do something like iterative numerical optimization, and then we would probably end up down here in the minimum location of this quadratic error surface. And this would be this guy here, this blue guy here, with an even smaller loss, and this would be optimal because, because it is, right? And it's not hard to find this because we now have this convex shape. Don't want to really deep dive too much into numerical optimization here, but because this is a really easy quadratic form, we have no problem optimizing this in one go by methods like gradient descent, for example. We could use that, could even use something that's maybe a bit faster in terms of numerical optimization, but it turns out we actually should not numerically iteratively optimize that because there is an analytic solution available to us, right? Because if this is a quadratic form, what we can also do is we can simply compute the derivative with pen and paper, then set this derivative to 0, and then try to solve for theta. And it turns out if the objective function or risk function is a quadratic function, right, then the derivative of that guy will be a linear function. And if we set a linear function to 0, we can easily solve that, right? Because solving it just means solving a linear system. And if we do this with pen and paper, and if you have never done this yourself, I heavily encourage you to do this. There's also a deep dive available here in this lecture where we'll do this together with you. And you can take a look at it, but I highly encourage you do this yourself before you look at that video, because this is a very, very good training exercise, and this is as easy as it gets in machine learning. For many of the upcoming models, these numerical optimization problems will be much harder, and this is it's a very good example exercise to get your hands dirty and understand the underlying concepts better. So if we do that, if we take the derivative of this guy with respect to our parameter vector theta, set it to 0, and then solve for theta, then we arrive at this equation here, which is a very, very compact form to immediately compute our optimal parameters theta hat in one go. So we do x transpose times x, we invert that, times x transposed again, times y, and that computes our optimal vector without performing any form of iterative numerical optimization. Little side note, we never invert these matrices here, and we will actually do something like this, solve a linear system instead. Maybe this is a somewhat advanced comment here at that stage, right? Rather solve it like this. We would ask for the solution to that linear system. Numerically, we usually don't want to invert matrices, I guess I'm venturing into territory here that I don't want to cover in this introductory course. Well, that brings us to the end of our slide set. So this is just a summarizing slide about the statistical properties of the linear model, which I do not want to cover here too much. So let's just kind of briefly look at them together. So if we now introduce the linear model more from a statistical perspective, I guess we would say that all of our data points are IID. Well, we are doing that from the ML perspective as well. But we would now not really start from a loss function. How do we measure errors? But we'd rather say, hey, how so there's we would probably say something like there's an underlying true relationship, and we're assuming that this true relationship is also linear, and then there are some random errors on top of that relationship, some measurement errors. And now we usually make an assumption about these measurement errors, and one of the simplest assumptions might be that these errors are actually Gaussian, so they are normally distributed with a certain variance, and then we can derive from that our y's, our y variables are also random variables. They are conditionally independent given x, and they are also normally distributed like this. And then we can derive our optimal estimators theta hat from that perspective. So more from a stochastic statistical perspective. It turns out that both of these approaches, starting from a loss function or starting from these error assumptions, are completely equivalent. So there's really no difference between statistics and machine learning in that regard. It's just two different, completely equivalent ways of looking at things, and which at the end result in the same type of maths and in the same formulas. But this we will study much later here in the lecture. And if these assumptions now hold, well, there's, I guess, if all features start to become super correlated, then this multicollinearity can become a problem, and this can destabilize our theta estimation. And so I don't want to go into this. If all of these assumptions here hold, or if they at the very least approximately hold, because they never truly hold in practice, but if they approximately hold, then we can do all of these nice inferential things on top of the linear model, right? We can do hypothesis tests on the significance of effects, including p-values. We can compute confidence intervals. We can compute prediction intervals. We can look at goodness of fit measures and so on. We can potentially associate our linear model with the correlation between the features and y and so on, because that's when we can talk about the part of the data variance which is explained by our model or which is not explained by our model by looking at this R-squared measure here. All of this you will cover in a traditional statistics course, and I will stop here. I hope you enjoyed this. See you in the upcoming lectures.